All right, so Unit 4, first section, Methods of Data Collection, Experiments and Studies. So in this section, we're going to talk about the different types of studies we can do, and then we're really going to focus on one of those, which is the experiment. We're going to talk about why we like experiments, what we can use them for, and the different things we want to avoid during an experiment, and how we can avoid them. So first of all, a study is a process that collects and analyzes data. So we're going to collect some data and then we're going to analyze that. That's what a study is. So there's 4 different ways that we can get our data for a study to analyze. So the first one I would say would be using available data. So if I go online or I open up a book or I go to the library and I look at data that's already been collected for some other purpose, I'm using what we call available data or secondary data because we're using it for a secondary purpose. So here I would write available data is data previously collected for another purpose. And there's lots of places we can go online and get old data to use in new studies. The next one I'll look at over here is anecdotal data. Anecdotal data is data that comes from a very small sample. Maybe even just one piece of data or less than 10 sometimes. And since it's such a small sample set, it does not represent the entire population very well. Does not represent the population. So in Apex, they give a lot of examples about people that say, oh, this business was horrible, or this brand of car is horrible, or this other thing is horrible because their sisters said that theirs didn't work right, or their brother said that theirs broke down, or they went to the store and they were overcharged. All of those conclusions are based off of one event, one piece of data. So it's more than likely that one event is not very representative of the entire population, okay? One bad visit to the grocery store doesn't mean that grocery store always operates without thinking about customer service. So anecdotal data is not what we want. Anecdotal data is not representative of the population. So if we go and look at available data, we want to make sure that the data that we're looking at does represent the entire population that we're interested in analyzing. Okay, if we want to collect our own data, we would be using one of these 2 methods, either an experiment or an observational study. And the way we know which one we want to use is whether we're trying to decide if something causes another or if there's simply a correlation. With observational studies, we can only talk about correlations between variables. Whereas with experiments, we can actually talk about cause and effect. Okay, we can say that one thing causes another if I produce an experiment that shows that it does. So in an experiment, what makes an experiment different from an observational study is that we actually apply a treatment. Apply a treatment or more than one treatment. So when we're applying a treatment, we are trying to manipulate the outcome. We are trying to get a certain response. So we could maybe apply an experiment where we have hamsters and we feed them different kinds of food. Or we can have an experiment where you have students and you put them in different math classes to see which class does better on SAT. You can look at people and you can give them different medications to see which one does better to prevent diabetes. As long as you are applying some sort of a treatment, you're trying to control the outcome, then you are performing an experiment. And with an experiment, our response variable is always what we measure at the end. So our results are measured, and that's where our data comes from. Measured after treatments. So our data in an experiment comes sometimes before and after a treatment is imposed on a set of subjects. In an observational study, we don't do anything to manipulate what happens. We simply collect data from a sample, and we can do that by observing and measuring, or we can do a survey. But the key thing here is that no treatment is imposed. We do absolutely nothing to make us get a certain outcome in an observational study. Okay, the next thing on here is with an observational study, we have two different outcomes here. We have a census and we have a sample. So if I am creating a census, that means that we're collecting data for every single individual in a population. So data is collected for every individual in a population. So as you know, right now, 2020, they're doing a census. The US government does a census every 10 years, and the purpose of that census is to collect data for every individual in the population. Okay, if sometimes though, of course, it can be very expensive, very tedious, very time consuming to try to get data for every single individual in a population. So in most cases, that's when we would get a sample instead. So if we're doing an observational study or an experiment on a sample, that means that data is being collected on a subset of the population. And that's what we usually do because, again, conducting a census gives us the best data, but conducting a census can be very time consuming and can be very expensive and sometimes even impossible. Okay, let's focus now on experiments. Experiments are what we have to perform in order to prove that there is cause and effect occurring between two variables. So with the experimental design, if you're asked to describe your experimental design, it means you need to describe how you have chosen your treatments. And describing how subjects or units are to be assigned to those treatments. So you would say, all right, so the treatment is going to be that we're going to give half of our individuals an experimental drug. And we're going to choose how people are assigned to the experimental drug or to the placebo using a random number generator. And we'll talk more about that later. So why would we want to conduct an experiment? As I already said, it's the only way that we can establish cause and effect between two variables. So that's the biggest reason. It's also, though, if we wanted to compare two groups on response to treatments. In order to talk about response to treatment, we have to impose that treatment, and so we would be doing an experiment. Overall, we are wanting to achieve generalizability, meaning we want to apply findings to the larger population. So when we're performing an experiment, we can only perform an experiment usually on a sample. But with any sample data, we want to hopefully be able to make predictions about the entire population when we're done. That's generalizability. If I can apply what we learned to the whole population, then we've kind of met our goal. When we apply our findings to the whole population, well, we're also doing what we call making an inference. Talked about inferences before and inferential statistics. Making an inference is when we apply what we learned from our study. The treatments in an experimental study are applied to experimental units. So whatever we're applying treatment to, that is what our experimental unit is. So if I'm giving medication to people, my experimental unit would be called people. And we actually usually call people subjects in an experiment. If I'm I'm applying electrical currents to bacteria, then my treatment would be the electrical current, and my experimental unit would be the bacteria. Since bacteria is not a person, we would simply call it a unit. In any experiment, in any statistical study, a bivariate study, of course, we have explanatory variables and response variables. Remember from the last unit that explanatory variables are X variables. There are independent variables, and response variables are Y variables. There are dependent variables. So in an experiment, the explanatory variable are the factors of treatments in an experiment, and the response variables is the measured response after the treatment is applied. So here in this picture, we have a study where people are being given aspirin and acetaminophen. So our factors of our explanatory variables are the aspirin and the acetaminophen. So this explanatory variable consists of two factors. And within those two factors, there are different levels being applied. So a level of a factor refers to different variants in the factors. Okay, we don't always have different levels. On a lot of experiments, we could just have everybody be getting one specific treatment or another. In this case, you can see the levels of our factors are actually doses of medication. So we have multiple dosages being prescribed, and therefore we have multiple levels of these factors of our explanatory variable. All right, so before we talk about how to have a good experiment, let's talk about what we want to avoid. What makes an experiment bad? The first thing is bias. Bias is error that encourages one outcome over others. So bias can simply be because of somebody's opinion. If we allow somebody's opinion to drive our study could result in bias. If we are doing an observational study and we only collect data from people who are very liberal, we would not get a very good representative of conservative people, and our data might be biased. If I was collecting data on income and I only interviewed people from a certain neighborhood, my data would be biased because it wouldn't be representative of people who lived maybe in a lower income neighborhood or even a higher income neighborhood. Bias can also happen just by an experimenter knowing what's happening, or by a person in an experiment knowing what's happening to them. Another thing that we'd want to avoid in experiments is chance variation. Chance variation is when the results of an experiment are due to chance. Often this happens because the experiment wasn't performed on enough subjects. So sticking to like a basic observational study, if you roll a die 5 times, it's possible that you could get just 1 or 2 numbers instead of 5 different numbers. That doesn't mean the probability of rolling that 1 or 2 numbers would be higher than any other number. It just means you didn't roll the die enough to see the true probability of rolling a number on a die. The same thing can happen in an experiment. If I perform an experiment on just 10 people, I'll likely get an outcome that isn't really representative of the whole population because I didn't perform my experiment on enough people. That's chance variation. It just happened by chance. The next thing is the placebo effect. You've probably heard of this before. Placebo effect is when subjects believe that they are receiving a treatment and they experience results. So psychologists do this a lot, where if somebody really thinks that they're sick, they'll prescribe them a sugar pill that doesn't actually do anything, but because the subject thinks that they're receiving medication for their anxiety, they feel better. That's the placebo effect. It's thinking you're getting some sort of a treatment and experiencing results just because your mind is in that place. So we want to avoid the placebo effect in our experiments. We don't want people to have results just because they know what the intended result should be. So in most cases, when we're performing experiments on people, we don't let them know what we expect the outcome to be. The next thing here is lurking variables, which causes confounding and is also sometimes called confounding variables. Lurking variables are variables that you aren't aware of that affect your response variable. So if we're talking about things like a plant that's growing and we're recording the growth at different times for different plants, things that we might not take into consideration might be how much sunlight one plant is getting, how much water it's getting. Maybe a dog came over and peed on one of the plants and made it stop growing. All kinds of things can come into these problems and affect what's happening. So there's always lurking variables, and we can try to predict what those lurking variables might be and then control those lurking variables. But in a lot of cases, there's going to be more lurking or confounding variables that we might not even think of. So we have some ways to kind of help avoid that happening. The next thing is the Hawthorne effect. The Hawthorne effect is when people change their behavior just because they know that they're being observed. For instance, if a teacher is teaching the way that they normally do every single day, but then the principal walks into their classroom, they tend to act a little bit different. Students do the same thing. When you're in your bedroom and you're talking to your friends on your cell phone and you're doing whatever you do, maybe playing games on your Xbox, and then your mom walks in, you're probably going to act a little bit different because you're being observed. The same thing happens in experiments. Oftentimes, if somebody knows that they're being observed, their behavior will be slightly different than it would be if they weren't being observed. That's the Hawthorne effect. So we want to avoid all of these things in our experiments, and we have some ways to do that. The three main principles of experimental design are kind of the basis for how we avoid these errors and this bias in our experiments. So the three primary principles of experimental design are replication, control, and randomization. There's a lot of other factors to a good experiment and things that we can do to make sure our experiment goes well, but these are the three most common, most basic things that we should always think about. Replication reduces chance variability by repeating experiments on different subjects or under different conditions. I'll write that down. It reduces chance variability which is the random chance that you get a certain response, by repeating experiments on different subjects or under different conditions. So by repeating our experiment over and over and over and over again, we're producing more and more and more pieces of data that can help us to determine what the actual conclusion is. So when we repeat those experiments over and over again, we can either get new subjects or we can use the same types of subjects under a different set of conditions to see if anything would change and to represent more parts of the entire population. The next primary principle of experimental design is control. Control is how we account for lurking variables. Okay, in order to account for lurking variables, we need a controlled experiment. When we have a controlled experiment, it means that we have our subjects separated into at least two groups. One group being the treatment group. This is the group that receives treatment. And the other group is the control group. The control group either receives no treatment or it only receives a placebo. And of course, they can't know that they're receiving a placebo. And a placebo, if you didn't know, a placebo is when somebody receives something that appears to have medical properties, but it actually doesn't have medical properties at all. So it's like a sugar pill. So no medical properties. So if we're doing experiment on a new medication, our treatment, of course, would be that our treatment group would receive the actual medication, and our control group might receive a placebo that looks like the medication, but actually doesn't have any medical properties at all. It'd probably be like a sugar pill or something. So by doing this, we can account for any lurking variables. Next thing is blind here. Since people have the Hawthorne effect, where if they know they're being observed, and the placebo effect, where if they think that they're getting something, that they might act a little bit differently. We have this thing called a blind experiment, and then we also have a double-blind experiment. So in a blind experiment, obviously they know half of the people are getting the treatment and half the people are not getting the treatment. But in a blind experiment, the subjects of the experiment do not know if they're getting the treatment. So that's why, again, why we have the placebo. We give them a pill regardless, but they know there's a chance that they might actually be receiving placebo and not the actual treatment itself. By doing that, we can avoid that placebo effect. We can avoid people having a response in their mind based on the fact that they're taking a pill. So again, in a blind experiment, none of the subjects know who got the treatment or who did not get the treatment. The next step above that, though, is the double-blind experiment. In a double-blind experiment, not only do the subjects not know who has the treatment, but neither do the experimenters. Subjects and experimenters do not know who has the treatment. And this goes along with the fact that obviously the experimenter wants their experiment to be a success. They want to get a certain response variable so they're not wasting their time. So oftentimes they might accidentally, unknowingly have a bias towards a certain response and skew those results in a way that would make them unreliable. So in a double-blind experiment, neither the subjects nor the people who are performing the experiment know who really has a placebo or the actual treatment. And that can be done a number of ways. They can hire an outside person to distribute things and to help manage the treatment itself. But the people who are recording the results, those are the people who would not know who actually got the real treatment. Okay. Last primary principle of an experimental design is randomization. So randomization, it controls bias by randomizing. controls bias by randomizing. Okay, if we think about people's opinions, of course, if I can manage to get a sample where I have a whole variety of different types of people with different types of opinions, that's going to be the best case scenario for any kind of survey that I want to do about what they would think. So how can we randomize in an observational study or an experiment? We randomize in two different ways usually. We can either use a random number table, or our graphing calculator can be used to produce random numbers or generate random numbers with software or your calculator. And that's going to help us randomize our experiments. So we're going to do some more of this later on, but you've seen this before probably in like elementary school, where your teacher comes in and she points to a person and says, "You're 1," and then the next person says, "You're 2," and the next person says, "You're 3," and then she starts over, "You're 1, you're 2, you're 3, you're 1, you're 2, you're 3, you're 1, you're 2, you're 3," and then she ends up with these random groups, 1, 2, and 3. To get an even more random sample, what we do is we take our entire group of people or subjects that are going to be in an experiment, and we assign them all a number, 1 through however many people there are. And then we use our random number generator to generate the people that'll be in different groups. So we'll see some more of that later on. Okay, here's some more good methods for creating a good experimental design. Okay, one is matched pairs. Matched pairs matches groups on a list of factors and uses one group as the treatment group and the other as a control group. So in other words, if I'm looking at dogs and I want to perform an experiment to see how dogs digest their kibble, all right, and I have this whole group of dogs, we already know that there's lots of different breeds of dogs and there's lots of different sizes. And those different breeds, different sizes of dogs might have different effects on diet. So in order to control that lurking variable, that confounding variable, it would be good to use a matched pairs design. Meaning, for every Chihuahua in group A, I would want another dog in group B that either is also a Chihuahua or is another small dog of the same size. If I have a Rottweiler in group A, I would want either another Rottweiler in group B or some other dog that's kind of the same size, like maybe a German Shepherd. Same thing with people. If I am measuring things with different people and their gender, age, and income might affect the response variable, I would want to make sure that I have those things matched up. I would say, okay, if I have a 9-year-old boy that lives in poverty in group A, then I would want to try to have a low-income boy in poverty also in group B to match that. Another way that we can do matched groups is to actually match people to themselves. Meaning, you take one person, you measure whatever you're wanting to measure, like maybe you're measuring their weight, and then you perform your treatment. You give them a diet supplement. And then you measure them again after that treatment is complete. Then that person is the control group because they were measured without the diet program, and they are also part of the experiment group because they were measured after they took the diet supplement. So those are the two ways we can do match groups. We can try to match people to their equivalents, or we can use people in both the control group and the treatment group. We just do their measurements before and after. So matched groups can be the same individual with measurement taken before and after. In matched pairs, the response variable is called the gain score. Okay, so since we know that we're going to have some variation between individuals in these things, like going back to people, if I have a 9-year-old little boy in low income and we have a 35-year-old woman who lives who is very wealthy, they're obviously going to have some different measurements in areas. But if I only look at their gain score, then those should be pretty comparable. Gain score is when I take their measurement after the treatment and subtract from that the measurement for the treatment to see how much it has changed. So going back to weight supplement diet pills, if I measure somebody's weight before and after they've used this weight pill, the difference in weights is the gain score. So anytime we're using matched groups, our response variable should be the difference in the two groups of the people that are matched, or in the two groups for the same person before and after treatment. And again, matched groups can be used both in experimental studies as well as observational studies. Matched pairs is also one of many different kinds of blocking. So blocking is just grouping subjects according to a variable that may affect a response variable that we are not interested in studying. So again, if we're going to study weight loss for a certain weight supplement, we know that men and women already lose weight in different ways, and different supplements have different effects on men and on women. So in that type of a study, it might be smart to block your groups by gender before assigning them into treatment and control groups so that we don't have too much variation within those sets.